Welcome back to another lesson in R. Today we're going to be really focused on the generalized random complete block design. But before I go into talking specifically with lesson 4 example, the reaction time, I want to bring us back to the insecticide example and how it would look if we performed the wrong analysis on it. So let's recall real quickly what the insecticide example is. Researchers were conducting an experiment to compare 3 different insecticides where we had 4 different blocks. Remember, in this random complete block design, we only have 1 replicate per treatment block. Okay? And here is the RCBD model. So we have our treatment and we have our block. So if we were to come to R, this only will work in my computer. It's telling me that I'm going to the right directory. I'll remove it for yours. But let's look at this. We're going to import our data. We're going to convert the treatment and block to factors. And we're going to run the correct ANOVA, where this is our alpha I and this is our beta J from here. And if we do this, we'll see that we have a treatment, we have our block, and we have this residual error row. This is the proper ANOVA. But let's say we had this insecticide example, but now we're going to run this generalized random complete block design, and we want to incorporate this interaction term. So what that's going to look like in R is we're going to have our treatment, which is our alpha I, our plot or block, which is our beta J, and then right here, treatment times block is going to represent this interaction term. And if we were to run this, let's go incorrect, boom, boom. Notice we have our treatment, we have our plot, and then our last row is this treatment block interaction. And we actually don't even have a row for the residuals. We also don't even have f-tests and p-values for our treatment and our interaction, which we saw in lesson 4. This is telling us we have something wrong. And what's happening is we are using all of our degrees of freedom in this model, and we have 0 degrees of freedom to estimate our residuals or our error. Okay, so this is a great indicator that you're using a generalized complete block design on a randomized complete block design. Okay, now let's talk about lesson 4. Now let's talk about lesson 4, where in lesson 4 we were focused on the reaction time under the influence of alcohol, where age is thought to be as a factor that could affect time. In each age group, each treatment, 0 ounce, 1 ounce, and 2 ounce, was randomly assigned to 4 individuals. So this is telling us we have replication, and so we can do the block treatment interaction. We have 4 replications per treatment in each block. So first, we're going to read in our data, and then we're going to convert to factors. Let's also look at what our data is. I had already done the view data prior. This looks right. Notice that, in a kind of a forewarning to your homework, your treatments are A, B, C, D, something like that. I would recommend that you also still convert that to a factor. It might, when you read it in, it might come in as a character, and then you'll have issues here. So just trying to forewarn you guys with that error. So again, the generalized random complete block design has our treatment, our effect, and our interaction. So we have our treatment alpha for alcohol, our block for the age, and we have the interaction. So if we were to run this, we get our summary, and notice how that residual row comes back into play, unlike it was in the incorrect insect ANOVA. So that's how you do your ANOVA. The next thing that we'd want to look at is, we looked at the interaction, we saw it's significant. The next thing you would typically look at is the block treatment interaction. But I'm going to do things a little bit backwards and talk about the main effects plot first. because I'm introducing a lot of new notation here and new code, and it will be easier to go and look at the treatment means and then the block treatment. But if you were doing the analysis, you would do the block treatment first. Okay, so in lesson 3, we did a for loop to find the estimated cell means and the overall treatment effects. Here I want to introduce something that's a little bit newer and keep you guys learning new stuff with R. So we're using what's called a split function. And what this split function is going to do is it's going to split the reaction time, our response, based on our alcohol level. So let's just copy and paste this. And notice that here are all the responses for when alcohol is 0. Here's all the responses for when alcohol is 1 and respectively for 2. Now what we're going to do is for each of these lists, we're going to apply the mean function, and we're going to get one value for each of these. So control copy, and that's what we're getting. So here's the treatment mean for 0 ounce, 1 ounce, and 2 ounce. We're going to save that into a variable, and we're now going to look at our main effects plot. This right here is just giving us 0, 1, and 2, our treatments, our title, this type B is telling us I want both the point and line. This is just some aesthetic stuff that makes me happy. We have our Y label, our X label. Now, notice that we have 0, 0.5, 1, 1.5, and 2.0, but really in our case, alcohol wasn't continuous, it was more discrete. And to represent that, we're going to add this argument, and what it's going to do is it's going to remove your x-axis, and then we're going to put in our own x-axis. So at 0, 1, and 2, I want labels 0 ounce, 1 ounce, 2 ounce. And so boom. This isn't necessary, but maybe it's something that you would want to do on a research paper or publication just to make your graph look a little bit cleaner. Okay, now with that in mind, let's go to our block treatment interaction. So up here, we were splitting the time based on alcohol. Now, for our interaction plot, where we're trying to do our estimated cell means, we want to split it based on alcohol and age group. So how we do that is by doing this list variable. So we're going to split time by these two variables. Show you what it looks like. Boom. Now notice we have a 0.1, 1.1, 2.1. The first number here is represented by our alcohol treatments 0, 1, 2, and the second number is represented by the block. So let's take this one for instance. This is the alcohol of 0 ounces in the third block. This is alcohol of 1 ounce in the third block. Then we're going to apply and find the mean for each of these block treatments. So we can look at our estimated cells, and then we have that. Now, there's one thing I want to note. The way or the order that you put these variables in is going to impact these numbers. So what we did was alcohol first and then age group, but let's just look at this different way of doing it, where we're going to do age first, then alcohol. So we're going to split. Now notice we have 1, 2, 3, and all 0. So this 1 is represented with block 1 and treatment 0. This is represented block 2, treatment 0, block 3, treatment 0. So the way that you order these variables is how this notation is going to be affected. So if we did our sample of our differences and we looked at it, we now have 1 block with 0 treatment. The estimates don't change if I was in, so here's block 1, treatment 0, if I was in treatment 0 block 1, the estimates aren't changing, but the labels on how you are is what is changing. Okay. I personally prefer doing it this way. It goes back to our notation where we have our mu I j, where I is the treatment and j is the block. Personal opinion. Now we're going to go to our interaction plot where we have our x factor, which is our treatment levels, and our trace factor, which is going to be our blocks. Now, what this right here is going to be representing, if we look back at our estimated cells, which is what we're going to use, we have 0, 1, 2, 0, 1, 2 for the treatments. And so all this is doing is it's giving me a vector of 0, 1, 2, 0, 1, 2, 0, 1, 2. I also need to convert it to a factor just because that's how this interaction function works. Here, the trace, it's all about the block, and our blocks are ordered 1, 1, 1, 2, 2, 2, 3, 3, 3. And then we have our response. And I'm going to drag this over so you can see that it matches. Now notice, if I use this differ value here, then these values would have to change because, let's look at differ. We would then have to go 1, 1, 2, 3 for the trace. 1, 2, 3, 1, 2, 3. And 0, 0, 0, 1, 1, 1, 2, 2, 2 for the X factor. I might put that code in just to give you guys an example. Alright, but that's how you do the interaction plot. Now the next thing that we looked at in lesson 4 was talking about contrasts. Specifically, we were talking about this contrast where we talked about how we got this L. So what happened was we took these alpha terms, brought them over to this side, so we have this. And then our contrasts were -1, 2, -1. To do just the treatment effect contrast, it's very similar to what we've done before, where we run our library. We're going to run this option right here. I don't want to get into the details of why we have to run it for the generalized and not the other ones that we've done. So we're not going to get there. Please just run the code. Trust me, it will match. And then this all right here matches, where this -1, 2, 1 are coming from our contrast coefficients. So if we were to run this warning right here is the same warning I gave to y'all in class, which was be careful that you're doing this treatment, make sure your interaction is significant, make sure we have co-directional and all that. Then we'll notice that we have the same t and our p-value is pretty low. Another approach, which would match more of your jump users, is to do it with the contrast coefficients to be -0.5, 1, and -0.5. And the reason we can do this is because we can take our contrast coefficients and multiply or divide them by a certain scale. And so what I did here was I divided this by 2, and so I got 1/2, 1, and 1/2. We run this. Really what the difference is going to be, let's see if I can get the result all one, is the estimate and the standard deviation are going to change. And that makes sense if we go back and we think about how these the contrast test is formulated, but our t and our p-value are the same. So it doesn't matter. This will get you something closer to jump. So all the same. Our next thing that we looked at was treatment effect within a block. And so how this differs, so this was looking at the main effects and seeing if this slope differs from this slope. Now what we would want to look at in our last example for this lesson was the treatment effect within a block. And really what we looked at was, does this slope in block 3 differ from this slope in this other slope in block 3? The issue that I found was that R didn't have like a good function or a package. And so we're going to have to do this more by hand, and I'm going to try and walk you through it the best I can. And if you have any issues or questions, please post on Slack or come to office hours and we'll correct everything. Okay? So, how do we do the block treatment contrast in R? I first set it up so that we're putting in our number of replicates per treatment within block, our number of treatments in our block. So we're going to control and we're going to run that. These are going to come into play down here. Then we're going to have our contrast coefficients. And our contrast was for the 0 treatment, we're looking in the third block. Treatment 1, third block, treatment 2, third block. And we have the same contrast coefficients as previously stated in lesson 4. We then have to estimate our L hat. And so how we do that is by getting our contrast coefficients and multiplying it by our estimated cell mean, which we already have. Now, where does this 7, 8, and 9 come from? Well, we want to look very carefully at how we have our estimated cell means. We know that we want the estimated cell mean for the 0 treatment third block, which is this one, which is also the 7th value in this vector. So 1, 2, 3, 4, 5, 6, 7. And so if I copy and paste this, it's going to get me this value. Notice it also does post the little header. Then we want to go the next contrast coefficient times the next cell mean, which again will give us this value right here. And again, repeat. Oh, I haven't ran these numbers. So run those numbers, and we're going to get an L hat. Then our next step is to create our sums of squares. So that's going to be n times L hat squared divided by the sum of the contrast coefficient squared. Our n from above, our L hat, which we just calculated, and then the summing of our contrast coefficients after they're squared. Boop, boop, boop. Now our MSE is going to come from our ANOVA table. So if we re-look back up our React ANOVA, we're going to go to our residuals and we're going to get our MSE right here. Now recall, our MSE is an estimate for our variance, and so if you wanted the standard deviation, which you don't in this case, but if you did, you would take the square root of this value if you wanted the standard deviation. We're going to control run this. Then you're going to calculate your F stat, which is your sums of square contrast divided by your MSE, and then we're going to print it. It's a little bit different, but it's really close to what we got with the jump. Then our degrees of freedom are going to be 1 for the numerator. Degrees of freedom for 2 is b times t, n minus 1, and then you run this code to get your p-value if it's a two-sided test. Now, I try to make it so that when you do your homework, if you adjust these variables, you'll have to adjust your contrast coefficients, and you will have to look at figuring out which estimated cell means, and that should be pretty simple. Look at your ANOVA table, but doing the F test and the p-value should just be copy and paste. So you will have to do a little bit more work than our jump users, but I think it's really cool that you guys are learning R. So again, you're going to have to change these values in yours. If you need help, come to office hours or ask on Slack, but calculating your F and doing your p-value should just be a copy and paste. Now the last thing I want to talk about is how you would do a Tukeys, and Tukeys is the same thing we've seen before, where you have your treatment and Tukeys. Control copy, paste, just to show you. That's it for this lesson. Have a great day.